So, hi everyone, my name's Claire Nelson. I'm an upcoming junior with a civil engineering major and a green building minor. This summer, I was exploring the mechanical properties of mycelium-based materials, and more specifically, how those properties varied with water hardness. So, let's talk about fungi. When you guys think of fungi, you're probably thinking like, oh, mushrooms. But I'm actually talking about a slightly different part of fungi called mycelium, and it looks a little horrifying, but this is the underground part of fungi. So, mycelium is the vegetative section. It's like the part that does not participate in reproduction at all. And like I said, it grows underground and it forms this really complicated 3D branching network of these like thin white fibers called hyphae. So hyphae, their basically role for fungal growth is to break through the soil to get to these different pockets of nutrients. So as you can imagine, breaking through the soil, they're a pretty strong material. And one of the most important things to note is that every different strain of fungi has a slightly different mycelial network. So all of them kind of grow in different ways, branch in different ways. Some are grow farther, some grow faster. So it really depends. Um, but why does any of this really matter? Well, it's because you can make almost anything out of this mycelium material. And you might think I'm exaggerating, but there's companies like Ecovative, MycoWorks, and even artists that are making mycelium leather and insulation, packaging, and even chairs, lamps, archways, stuff like that. Um, so mycelium materials are capable of doing all of these different things because the final mechanical properties completely depend on the type of fungi that you choose and also the type of food that you feed it. So, how this works is you have like your fungal strain, and then it basically decomposes and binds around basically any sort of agricultural waste product. So it forms this like nice solid material. And that completely depends on the strain, the food that you feed it, and also the like temperature, humidity, amount of light that you give it when it grows. So also like another important thing to note about mycelium is that it has great potential to decrease the amount of organic matter that we're putting into landfills these days. Repurposing agricultural waste for the purposes of feeding a new material is much better than letting it decompose in a landfill where it's going to pollute the air as it releases methane, pollute groundwater as the leachate leaks through the landfill lining, stuff like that. And as a civil engineer, looking at the construction industry's impact on um, especially like air pollution with its carbon emissions every year. Um, New materials with more sustainable production processes are very desirable. And it kind of makes sense, but the construction industry uses more raw materials than any other economic activity. So finding new materials with growing populations and more need for public infrastructure and like viable housing, finding new materials to kind of contribute to that is definitely a desirable thing. Um, and also, this type of material needs research. This There's over 30,000 viable species of fungi that you could use, and even then, the material is going to change depending on the food that you give it and the conditions that you grow it in. So this is definitely a new blossoming area of research. Um, So just this is a general summary of what I was talking about before about why this is a really awesome sustainable material. So what I did this summer, or I was hoping to do, was explore mycelium's potential as a sustainable alternative to current construction and design materials. And I also wanted to test varying growth conditions to see how it affected the final mechanical properties of mycelium. Um, so the actual variables that I was interested in testing were how like a nutritional boost, like some sort of yummy carbohydrate, would increase the growth of the mycelium network. And I was also curious if different water hardnesses, so like adding more minerals, if that would increase the strength of the final network. So just generally speaking, I chose the fungus Trametes versicolor, which is called turkey tail. You guys might have heard like seen it on hikes and stuff. It grows off of dead logs. Um, And for my fungi food, I chose hemp stalks. So I got them from a farm in like southern Vermont. And then I combined the fungi with the sterilized like food and all the different hard water combinations in grow bags. And then I incubated them for a set amount of time. I added the nutritional boost, which was one of the variables I was studying. Um, and then I stopped the growth of the material by heating it in the oven. A lot of the times people get concerned about fungal materials because they think, oh no, like I don't want to be breathing in fungal spores. But all of these materials are dead in the end. You have to stop the growth. And then I had some testing procedures that I wanted to do. So just generally, you choose your strain, choose your food, you get your fungi, and then you combine it all and let it grow for a set amount of time. Um, so unfortunately, I had a few unexpected errors in my experiment. So there was a bit too much moisture in the grow bags. I was following some of the previous procedures that have been done in this realm, and it was just way too much water for what I was doing. And also, due to some shipping delays, the actual fungi that I was using ended up drying out and died before I could add it to the bags. So this could have been the end of my research, but I still had these hemp materials, even though the mycelium hadn't grown around them. As happens with biological work, things die. I still had these hemp materials, so I decided to study them anyway. So the first thing I looked at was the water absorption rate. This is super important when you're looking at applications for like insulation and particle board and generally just like interior materials. Um, so give me 1 second, sorry. um, so the water absorption rate generally, if you look at this graph on the bottom right, it increased as the water hardness increased. This could have been due to a variety of factors, potentially like the minerals when they hardened in the mass made it these little water pockets that were able to catch water easier, but I'm not exactly sure. Um, but the important part is that on the left over here, you'll see that they reached all the materials, all the samples I tested reached their peak absorption pretty quickly, which means that they're not exactly ideal for interior materials. If you look at these like orange kind of shaded areas, that is what a mycelium material ideally would be in that range. So hopefully in the future, I can grow this mycelium kind of coating because mycelium is naturally hydrophobic, and that will kind of get these hemp-based materials into the range of what could be used for some sort of like insulation. And the next thing I tested was the compressing strength. So if you're used to looking at stress strain curves, this one definitely looks pretty weird. Typically, curves look like this. They are going to have some sort of peak that's like the failure point of the material. But these ones just kept compressing, almost like some sort of sponge or rubber material. Just for a comparison, this is what a rubber like load distribution curve looks like. So if you look down here, like before 100 seconds, the air was just getting compressed out. And then after 100 seconds, the material actually started taking the load. So here is what it looked like. As you can see, it is very spongy. At the end of this video, it has about the equivalent of 10 people standing on it. So this is not at all the material that I was expecting to be studying. I was expecting a mycelium material, which usually does have like a fracture point in compression tests. But I still came up with some potential applications for it. For example, packaging. As a replacement for potentially styrofoam, this kind of like spongy material would be incredible for keeping fragile materials safe during shipping. Also, potentially for padded floorings, like in playgrounds or even like the mat in front of your kitchen sink. Also, rubber materials can be used in automobiles as padding, and if I did more research, it could potentially be this incredible insulation material. But the thermal properties would need to be explored a bit more. So overall, although I did not get to study what I wanted to, I did learn a lot about hemp and its properties, and it has incredibly natural binding properties. Mycelium was supposed to be the network that was going to hold it all together, but even though that didn't happen, the materials were still pretty sturdy. And in the future, if I was to actually grow like a viable fungal culture onto this material, it could have great potential for structural interiors. And also, I learned that you definitely need to be prepared to adapt. This research, as I said, did not go as planned, but I still found some some important factors that I could study. So I'm going to continue exploring this material with microscopy. Unfortunately, I wasn't able to coordinate that before this presentation. And I'm going to keep studying fungi so that hopefully I can design an honors thesis in the future. Because the material properties of hemp is really great, like preliminary research if I want to do a direct comparison between how hemp acts versus how hemp acts when it's been inoculated with mycelium. So that's all. I just wanted to thank my faculty advisor, Dr. Tintin, and Dr. Badaretti and Louis Zhang for their advisement, and also Kismet Farms, which is the place where I got the hemp. They very generously donated it to me.